Before we learned how to find limits analytically, what were the two ways that we found limits in section 2.2? By looking at a graph or by making a table. That's the two ways we could find limits in 2.2. But then we found out most limits can be evaluated by direct substitution. Just whatever number the x is supposed to be approaching, plug that number into the function, and if that value exists, that's the limit in most cases. We also found, though, that sometimes that direct substitution failed because you got what is called indeterminate form. You got something with a 0 in the denominator, and that blows up everything. It would be tempting when you get 0 in the denominator to go automatically, hey, the limit doesn't exist. But you should not automatically go, the limit doesn't exist, because sometimes that issue with indeterminate form could be resolved. And we talked about 3 tools, I don't like to call them tricks, but 3 tools for resolving indeterminate form. One was if you have a rational expression, just see if it can be simplified. If you can cancel out that factor in the denominator, then you won't have indeterminate form anymore. The second tool was rationalize the numerator. Sometimes that takes care of the indeterminate form problem, sometimes it doesn't, but you should try it. And then third, if you have a complex rational expression, you should simplify that. So most of last night's homework was algebraic. About half of the problems, the limit could be evaluated by direct substitution. About half of the problems, you had to use one of these 3 tools to resolve the indeterminate form. But now we have some problems that cannot be evaluated by direct substitution, and those 3 tools just don't apply. There are 3 special limits that, with a little bit of work, you will just learn to recognize, ooh, that's one of the special guys, and number 1 and 2 even more than number 3. Number 3 is cool because it's the definition of the number e, the irrational number e. I think when we did 1.6, I told you, hey, look for this coming. It's the definition of e. It's equivalent to the compound interest formula when $1 is invested at 100% for 1 year, compounded infinitely many times. When your money is compounded infinitely many times, that $1 gets closer and closer and closer to $2.78. We're actually not going to see that very much, though. What we will see is variations on the limit as x approaches 0 of sine x over x. That's equivalent to the limit as x approaches 0 of x over sine x. In other words, it doesn't matter which is in the numerator, which is in the denominator. That's one of those graphs that goes bounce. Well, no, I don't want to say that. That's not true. That limit is 1, and you can see that graphically or by making a table, but it's difficult to find that algebraically. To find that algebraically takes the squeeze theorem. I don't even talk about the squeeze theorem. I'm just going to say when you see the limit as x goes to 0 of x over sine x or sine x over x, that's worth memorizing. That is just 1. And the other special limit that's worth memorizing is the limit as x goes to 0 of 1 minus cosine x over x is 0. So if you just put those 2 limits in your list of things you have memorized, or list of things you want to jot at the top of your blank paper when you start the test. You have to start the test with blank paper, but then if you want to have a brain dump at the top, that's fine. Those will come in handy. Let's see how they will come in handy. You have 2 examples in the book. Example 9 and 10, you may need to refer to those as well, but the ones that I want to work are on page 88, starting at number 68. realized that there are some very relevant properties in the book that I didn't mention. I need to mention those before we do this number 68. On page 79, my handout did have those basic limits. The limit of a constant is just the constant. The limit as x approaches c of x is just c. And a power function can be evaluated by direct substitution. I have those on my handout. What I did not have was these. If you're taking the limit of a function multiplied by some number, that number is called a scalar. If you have the limit of some number times a function, you can just keep up with the scalar, the number, and take the limit of the function and then multiply those. It's almost like factoring out the constant. You can factor out, I don't even want to say that, it's not really factoring out, but you can keep up with the constant, find the limit of the function, and then multiply those. B says if you have the limit of the sum of two functions, you can just take the limit of each term. If you have a limit of a product of functions, you can just take the limit of each factor and then multiply those. If you have the limit of a quotient, you can just take the limit of the numerator and the limit of the denominator, as long as you're watching out for what makes the denominator 0. And then number 5, if you have the limit of a function to a power, you can just take the limit of the function and then apply the power. The reason I needed to mention those before we got to 68 was because on 68, we have the limit of a constant times one of our special guys, one of our special limits, 1 minus cosine x over x. I'm going to put in the middle step this once, and then I'm not going to put in the middle step anymore. If you have the limit of a constant times a function, you can just bring the constant out front and take the limit of the function. That limit as x goes to 0 of 1 minus cosine x over x is one of the special limits on the notes. What do the notes say that limit is? That's 0. So this is just 3 times 0, and 3 times 0 is just 0. That limit is 0, and you could find it, let me say specifically, the limit as x approaches 0 as 0. If x was approaching something else, the limit would be something else. But as long as x is approaching 0, that limit is 0. You could see that by making a table. You could see that by looking at the graph, but there's no way to fix that algebraically. You can't just plug 0 in the place of x. You can't just cancel the x's. There's no algebraic way to fix it, so that's one of the special limits you need to have memorized. Most of these are pretty straightforward. There's a couple of nice tricks we have. Let's see number 70. The limit as theta goes to 0 of cosine theta tangent theta divided by theta. Can I evaluate that by direct substitution? Nope, can't let theta be 0. Is it anything I can fix with one of my 3 algebraic tools? Not really. Is it one of my 3 special limits that I have typed in the notes? No. So we got to come up with something else. Can you think of any way that we could simplify that expression and just pray that that fixed something? Tell me what you think. We can simplify cosine times tangent. Now, I'm going to write in the middle step for anybody who needs it. If you can do this in your head and you skip the middle step, that's absolutely fine. But I don't want anybody to get home and look at their notes and go, what the heck? Tangent is sine over cosine And you can cancel those cosines. So this becomes the limit as theta goes to 0 of sine theta over theta. Is that one of our special limits? Yeah, on the front, I think in the notes I had x instead of theta, but it's just a variable. As long as you have sine of ugly over the same old ugly, as limit as theta approaches, or as ugly approaches 0, then what is that? That's 1. Again, it doesn't matter what the variable is. It could be something as ugly as sine of x squared plus 3x plus 2, as long as you had it over x squared plus 3x plus 2, and it was x squared plus 3x plus 2 that was approaching 0, then it would still be 1. If you had limit as duck approaches 0 of sine duck over duck, it would be 1. All right, let's try 72. This one's just takes a little more ingenuity. I definitely can't evaluate it by direct substitution. That's tangent squared x. I can't evaluate it by direct substitution. None of my algebraic tools help. Not one of my special limits. Somehow I bet it factors or something into one of my special limits. This is where you start writing in pencil, because you're going to try something, and if it doesn't work, you're going to erase it. You're going to try something else. You can't just sit there until God whispers to you. Got any ideas? Tell me something to try. All right, let's try that. And like you should be doing, I'm going to write in pencil just in case I have to erase. I'm going to say that's limit as x goes to 0. And you're saying write tangent square as sine square over cosine square. All right. That's certainly a reasonable thing to do. I don't know if it shows up as well when I write in pencil. That's a reasonable thing to try. I don't yet see how it helps me, but maybe if we did another step, it would suddenly pop out. Anybody have another idea?
Maybe change sine squared into 1 minus cosine squared.
I can see kind of why you're thinking that, because number one, it's true. It is a Pythagorean identity. Number two, the second limit theorem has a 1 minus cosine in it. So maybe that 1 minus sine squared, or that cosine squared minus 1 would factor into cosine plus 1, cosine minus 1. Something may end up canceling there. Just because I did this problem last night, I know that's probably not the easiest thing to do. It's absolutely legal. I'm not sure it would be helpful. There's something easier. Yes, sir.
Change it to 1 minus secant.
That makes me even more afraid. It's absolutely legal, but I tell you why it makes me more afraid. None of my special limits have a secant in it. I'm thinking the key is going to be to have this in terms of sines and or cosines, because that is what exists in my special limits. And I may be able to get there that road, but that one scares me. Anybody got another idea? There's another way we could rewrite that, leaving sine, sine, and leaving cosine, cosine. How else could I rewrite that? What's equivalent to that? That certainly works. Let's see. That's certainly true. The other question is it helpful? Do you have another idea, Glenn?
Let's say maybe multiply by the sign.
Okay, if I multiply by the reciprocal, I'd have to multiply both the numerator and denominator by the reciprocal, but you're getting warm there. You're getting really close. Is it bugging anybody that that's a complex fraction? That's a baby fraction within a big fraction. How do we fix that? Not multiply by the reciprocal, but multiply by the LCD, just multiply by the denominator over itself. I actually could have done that here. I could have multiplied by cosine squared over cosine squared. But we went down this road, so we'll keep going. What does that numerator become if I multiply by cosine? Do I multiply each factor by cosine? Is that what's about to happen? No, that's not, I'm sorry, that's not terms. If those were added, I would have to make sure I multiplied cosine times each one. But that's multiplication, and so this cosine is only going to cancel out one of those cosines. If I want to cancel them both, I'm going to really have to multiply by cosine squared, so that one of the cosines cancels this, and the other cosine cancels that.
But which is the easier to put it up there?
But we didn't know that to start with. Yeah, it would have been easier just to do that on the step above, but we didn't know that. So now we're a little better off, maybe. We have, I'm going to write that as sine square x over x cosine square x. And I keep looking at it and thinking, how close am I getting to one of those special limits? Do I see any way of separating that into something that's one of my special limits?
Sine x over x and sine x over cosine squared x.
I know that one of my special limits, great job. I know that one of my special limits is the limit as x approaches 0 of sine x over x. So I can just write that down. I can pull it out because I know that's what I want to have. If I pull that out, then I can just say, okay, if I get what I want, what will be left? And you're exactly right. If I get what I want, then what's left is the other sine x over the cosine square x. This, I know that when I have the limit of a product of two functions, I can just take the limit of each factor. So I can already evaluate limit as x approaches 0 of sine x over x. That's just 1. How about that other factor? Can I evaluate that as x goes to 0 by direct substitution? If I let x be 0, what's cosine 0? Oh, I don't have 0 in the denominator anymore. I have 1 in the denominator. And what do I have in the numerator? Sine of 0 is 0, so this is 0 over 1. That's not indeterminate form. 0 over 1 is just 0, and 1 times 0 is just 0.
All that for 0.
I don't know if I told y'all this or not. I think I mentioned it in pre-calculus yesterday. My husband is a biologist for TWRA, and I'm not sure why they're required to take calculus, but he had to take calculus at UT, and he came up with the Miles law of calculus, which is when in doubt, put 0, 1, or -1. That's the answer about half the time in calculus. Great. So just remember the Miles, when all else fails, default to the Miles law of calculus, and any, many, miny, mo, put a 0, 1, or -1. Glenn, what were you thinking?
I was gonna say, since there's that product rule, if you take x as it approaches 0, sine of x over x right there, so that equals 0.
No, that doesn't equal 0. That equals 1.
Yeah,
Yeah, look on the paper. That equals 1.
Yeah.
But
if that was one of the factors that equals 0, then you could just say that.
you would still have to watch out for indeterminate form, because even if this was 0, if that denominator is 0, there's still a problem. 0 times undefined is a whole other universe. Yes, sir.
If you were to take the sine squared x and change it into 1 minus cosine squared x, like he said,
Did you get it to work that way?
yeah, you still get 0.
Awesome. I was scared to try it, but you tried it and it worked. That's-
You have to multiply secant squared x, it's not 0. It's the special form, 1 minus cosine x over x.
I had a feeling it would work. I was a little timid about going down that road because I knew we were on a road that was gonna work. But you were brave and stuck to your own path, and yeah, I thought you'd get there. Good. Doesn't matter that you get there my way. It just matters that you get there. Now, is there any step that I could have skipped that would have made that shorter? Well, it just depends on how good you are at enabling trig functions in your head. I think that I could have skipped this step. I've had enough practice at trig. I might could have gone straight from here to here. I don't know. But you add in as many steps as you need, and don't be afraid to try something, because that's, in my opinion, the big difference between college algebra and then getting into calculus is college algebra, at least my college algebra, is still pretty much monkey see, monkey do. I do a problem, you do 5 like it. All of a sudden, pre-calculus became less of that, and calculus is going to become less of that. You have to try something. Either write in pencil so you can erase it, or plan on rewriting your problems several times so you hand me something readable for your homework. I hate pencils, so I did all my calculus in ink, but I did a whole lot of writing, rewriting, turning in ink homework. You just have to try something. All right, so what about 74? I love just saying this one out loud. That's the Greek letter phi. Let me finish writing it, and then I'm going to say it out loud. Here's how cool this is. The closest I'll ever come to speaking Chinese. The limit as phi approaches pi of phi secant phi. If that was politically incorrect, I'm sorry. I'm just saying, it doesn't even sound like English. Can you evaluate that by direct substitution?
I don't know.
I'm not kidding. I can't even think secant. You give me secant, I'm going to go, that's what? What is secant? 1 over cosine. So my first thought is, I don't want to deal with that. I'm going to change it to, if that's 1 over cosine, then this is phi over cosine phi. Is that one of your special?
Different variable in there.
Nope, you're gonna have to learn to work with fives. P5s, folks, funds. Is that one of our special limits? Can I just automatically say what that is?
Yes. No, there's no one mark.
Yeah, that's not, and, even though in this first one, it doesn't matter if you have sine x over x or x over sine x, you still get 1. I'm not sure that's true here. I'd have to investigate it, but I'm not sure that would be the same if you had the x in the numerator and the 1 minus cosine x in the denominator. I'd have to think about that. Yes?
That's what pi.
You don't need a special limit because that can be evaluated by direct substitution. Cosine of pi is not 0. That's pi over cosine pi. Just putting pi in place of 5. And what's cosine pi? Pi is 180 degrees, cosine is x, x is -1. This is pi over -1, which is negative pi. That's just fun. The limit of phi approaches pi of phi secant phi is negative pi. That doesn't make anybody but me happy. It makes Glenn happy.
Calculus never died.
That's right. I love calculus. I never believed I would say that. Cal 2 almost made me suicidal. But that was just me. That was just me. You'll be fine. You'll be fine. I had a sadistic calculus 2 teacher who liked to make girls cry. He did, and he did a good job of it. I cried a lot in calculus 2, but I think it was more him than me. If I'd had cool Dr. Spate, it would have been fine. All right. Let's skip. I'm going to skip to 78. I need to get 3 more problems done. 78. The limit as x approaches 0 of 4 times e to the 2x minus 1 over e to the x minus 1. First thing I'm going to think always is, can I evaluate that by direct substitution? No. In the denominator, e to the 0 is 1, 1 minus 1, 0, boom, it's gone. Any of my algebraic tricks work? Tools, not tricks. Is it one of my special limits? I know one of my special limits has an e in it, but it's not that, is it? It's just the limit of 1 plus 1 over x to the x is e. That has very little to do with that. All right, it's just going to be try something, and if it's not right, erase. Tell me.
Is e to the 2x power minus 1, is that a difference of squares?
It absolutely is a difference of 2 squares. Oh my gosh!
Way to go, Mike.
Must be nice. Be a nerd.
Nerds generally earn more money than non-nerds.
But I can use them.
How do you factor e to the 2x minus 1?
Ex minus 1 times ex plus 2.
If you're not sure, write it in pencil and check it. I am sure, so I'm going to write it in ink. But this is what you have to do in calculus. If you have an inkling of something that might work, try it and then check it. This e to the x times e to the x, when you multiply 2 expressions with the same base, what do you do with the exponents? You add them, and what's x plus x? It worked. Outer and inner gives you 0, last gives you -1. The more you practice, the more God will whisper to you. You just have to try something. Is that a limit you can evaluate by direct substitution? What is it? It's 8. How cute is that?
Just adorable.
Yeah, that's why it's 0, 1, negative 1.
I didn't say always, I said about
Jesus
the
loved
half
me a
the
long
time.
time ago.
About half the time. E to the 0 is 1. Hey, I'm losing you. E to the 0 is 1. 1 plus 1 is 2. 4 times 2 is 8. Can't believe it.
Why not just write 8?
All right. One more very interesting thing to think about, and then we'll skip to slightly different instructions. Number 80. Hey, y'all, knock off the chatter. This is going to take concentration here. Is this something I can evaluate by direct substitution? Probably not. It wouldn't be the last problem in the book if it wasn't hard. All right, so no, it can't be evaluated by direct substitution. Is it one of my special limits? Nope. Is it anything I can reduce? Can I somehow subtract the 3x from the 2x? Is that legal? No, that's not. There is a hint in the book if you happen to have your book open. I shouldn't have told you that. I should just make you squint and think a while. If that's not one of my special limits, what would be something that would be one of my special limits? If I had sine 2x over what? If the argument was 2x, the denominator would have to be 2x. If it was sine of 2x over 2x, I can handle it. What about sine of 3x? What would have to go along with that in order for me to be able to apply one of my special limits? It would have to be 3x. Here is a hint, a tool. I've already mentioned it once, but it's going to be really important here. When you can't think of anything else to try, put down what you want to have, and then think of a legal way to get that. What you just told me was, if this was sine of 2x over 2x, I could handle it. If this was 3x over sine 3x, I could handle it. But that doesn't multiply back together to give me what I started with. What does it lack in, what's there that's not supposed to be there if I multiply that back together in an attempt to get back what I started with? Actually, the x's would cancel each other. So it's just the 3 and the 2 that's problematic. That 3 in the numerator and 2 in the denominator is all I would have to fix in order to get back the thing I originally had. What could I do to that to cancel out the 3 and the 2 that I don't want? And you're thinking, is that legal? You can just multiply by 2/3? Well, my answer to that would be, is that equivalent to what's on the line above it? If it's equivalent to what's on the line above it, it's legal. The X's would cancel, the 2's would cancel, the 3's would cancel, and it would leave me back exactly what I started with. So it's legal. Not only is it legal, it is helpful because now I have the limit of 3 factors. I can evaluate each one of those separately. I could say the limit as x approaches 0 of a constant is just the constant. The limit as x approaches 0 of sine of 2x over 2x is what? That's 1. That's sine of duck over duck. And the last one's duck over sine of duck. The limit as x approaches 0 of that is what? 1. So what's that answer? Yep. What the heck? So the lesson, I think the lesson of today, 2 things. Number 1, make sure you know those 2 special limits. I would write them at the top of my paper when I began the test because I like being able to see them. I will recognize them better if I can flip my page over and, oh yeah, they are, there they are. That's what I need. That's lesson 1 for the day. Lesson 2 for the day is you gotta try something. And sometimes the thing you try is writing down your dreams. It's my dream. And then figuring out how to legally make it come true. That's a lesson for life. Write down your dreams and then find a legal way to make it come true. That's important. I'm not just going to say make your dreams come true. Find a legal way to make your dreams come true. This is what I wanted. This is what it took to make it come true. I know. Nothing else, you'll have great life lessons from me. Yes, sir, Major. Hey, Major's asking a question. Help be respectful. No. Let me show you, just to remind you of a couple things about trig. It is not true that sine of 2x is the same thing as 2 sine of x. That's what you're wanting to do, and no, that's not legal. That's finding an illegal way to make your dreams come true. All right, last set of directions. 92 and 94. Right here. Last 2 problems in the homework. Where is it? There it is. This expression is called, well, just the argument part, just the f of x plus delta x minus f of x over delta x, that's called the difference quotient. That's going to turn out to be something very, very important of calculus, probably the most important thing in calculus. When we say the limit of the difference quotient as delta x goes to 0, remember that I told you the definition of derivative could be written 2 ways. In some books, they use a delta x. In some books, they use an h for that little difference in the x's. This is just the limit as the difference in the x's gets smaller and smaller. That's what delta x means. It's like in the slope formula, if the 2 points are getting closer and closer together, that would be delta x going to 0. So for these 4 problems, and we may have time to do both evens, we may just have time to do one of them, but for both of them, we're going to find the limit as delta x goes to 0 of the difference quotient. This is just a recipe. This is just following a recipe. Do what the recipe says. So 92, the function is f of x equals x squared minus 4x. And the directions say find the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. You don't have to memorize it yet. But you have to be able to follow that recipe. What does f of x plus delta x mean? What does f of duck mean?
Substitute duck where.
Put the duck everywhere there's an x. That means put the x plus delta x everywhere there's an x in the function. Don't lose your limit notation until you evaluate the limit. I'm putting x plus delta x in place of both of those x's in the function. X plus delta x squared minus 4 times x plus delta x. That much is f, I meant to leave ring there and I forgot. That's f of x plus delta x. Everything that I've written so far in the numerator is what I obtained by putting x plus delta x in place of x in the function f. What does the recipe tell us to do now? This is the recipe. Put f of x, subtract f of x is what the recipe is saying. So subtract f of x is this guy right here. What very common mistake do I keep making in the hopes that when you get to the test you won't make it? If you're subtracting the whole function, then the function has to be in parentheses until you distribute that -1. So here's my f of x plus delta x. Here's the minus f of x. The recipe says divide all that by delta x. You shouldn't have to do this on your birthday. I agree. Right. Is that a limit I can just evaluate by direct substitution? Put 0 in place of all the delta x's? No, that'll give me 0 in the denominator. Does that look kind of like the problem you asked me about, Alan? Yep. We're going to have to fold x plus delta x. Don't lose your limit notation. X plus delta x is x squared. What will the middle term be after I combine like terms? 2x delta x. And what will the last term be? Delta x squared. If you can't see that without a middle step, then you need to write down x plus delta x times x plus delta x and FOIL it. But it would be better if you didn't have to do that. It would save you time. All right? Distribute that -4. And I just like keeping my delta x in parentheses so that I can see they're together. And then distribute the -1. My limit notation still over there. It's just off camera. Good. All right. As happens many times when you're evaluating the difference quotient, a whole lot of stuff cancels. I have an x squared minus an x squared. I have a -4x plus 4x. Is there anything else that will cancel in the numerator? Anything else that will give me 0 in the numerator? No. But what do all the terms in the numerator have in common? And so what can I do with that? Factor out a delta x. Don't lose your limit notation. You factor out a delta x, what's left of this first term? 2x. What's left of the second term that's left? Delta x. What's left of the third term? Cancel that delta x that I factored out. Remember, delta x means the difference in two x's. So what this is right now is our difference in two x's is so small that it just almost disappears. We can't say it totally disappears, but it's so that difference is so small it practically disappears. What's left of that function or that expression? 2x minus 4. Now let me say something important about that 2x minus 4. Chapter 2 is on limits. You can find limits now by making a table, by looking at a graph, by direct substitution. You've got some tools for resolving indeterminate form, and you have a couple of special limits you have memorized. But basically, you know almost everything I know about limits now. Chapter 3 is the derivative. I've been alluding to this all along. That is the definition of the derivative, whatever that means. And in the first chapter, section of chapter 3, this is how we're going to find the derivative. I'm going to give you all kinds of functions. You're going to follow this recipe, blah, 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 come up with a derivative. What you're going to love about either 3.2 or 3.3, I can't remember which one, is there's a shortcut in getting from here to here. That shortcut doesn't take any of that. Dizzy, you've seen it before. The shortcut doesn't take any of that, does it?
I don't remember.
Don't remember the shortcut? Yay! Then you'll be just as amazed as everybody else when you find out there's a shortcut. All right, homework is at the bottom of the page. There's a good chance that I will take up 2.3 tomorrow. So you make sure you get all of that done tonight. You should have half of it done already. Get the rest of it done.
Hey, real quick, what was 94?
What was 94? It was the same thing. Evaluate the limit, the difference quotient. Are you just asking what's the answer? I don't have it written down, but I know because of the shortcut, it would be 1/2 square root of x. Yes. But isn't it cool that, I mean, you went through the difference quotient to find that? I used the shortcut and got from there to there in my head. So you're going to love that shortcut again when you remember it.
Did like hours and difference quotients on the online class, maybe hate H.
You shouldn't hate h as bad as you hate delta x.
H ruined everything.
And then it just disappears.
No,
If you're finding the limit as h goes to 0, it does. Just something to look forward to, Disney. See ya. Hey, I didn't ask how did homecoming go?
Oh, it went good. I didn't win, but it was. I
A
was glad I
friend?
got to walk. Yeah.
Wonderful,
Yeah.
wonderful. I'm glad.
Thank you.
Hello, ladies.
I taught. Okay, I meant to, and then all of a sudden, after history, I had to leave. I was like, as soon as I was on there, I was like, oh man. And then last night I was like, oh man. Let's see.